So it's time to come back. So it's time to come back and add our last main circuit element, and so that's the inductor. So if you remember when we introduced all our basic circuit elements right up at the beginning, we said, what is an inductor? Well, it's a device for storing energy in a magnetic field, much like a capacitor is a device for storing energy in an electric field. So how do you make an inductor? Well, basically what you do is you just take some wire and then you just wrap it around. And so effectively what you're doing is you're with these wire windings, what they're going to allow for is they're going to allow for some, as current flows, that current generates a magnetic field. That magnetic field is actually going to establish a magnetic flux through the windings in the inductor. You can do it around an iron core, you can do it around an air core in the same way that we talked about with a capacitor. You can have just air between your capacitance plates, or you can have a dielectric stuck in there. So this is the same sort of idea. And what we care about, right, the quantity that we're going to care about, of course, is the inductance. So what is the inductance of an inductor? And that's going to be given by L. So what is it that the inductance is trying to tell us about? Well, sort of it's defined to be, this is again the magnetic flux over the current. So one of the things that we're going to do, because when you get to dealing with inductors, the currents and voltages are going to start to change within your circuit. So rather than being constant things, they're going to be changing things. So what we're going to do is we're going to use lowercase letters to denote things that will be changing. And so again, here I've got a current that can change, and then the ratio of the magnetic flux to that current defines what the inductance is. So you can think of part of what the inductance is telling you is it's telling you how much magnetic flux is your inductor going to have at a given particular current. And just like we talked about with the capacitance for a capacitor or the resistance for a resistor, this is something that basically depends on the geometry, the makeup of the inductor. It doesn't depend on how much current's flowing through it. So from Faraday's law, well, again, we've been sort of writing this in terms of an epsilon, right? So the EMF, and all we're going to do is say, well, we're just going to write it in terms of a lowercase v. It still means the same thing. It's the potential difference across the inductor. So the voltage of the inductor, again, if we're not worried about signs, I don't need to worry about the minus sign here, and this is just going to be d, the time derivative, so the derivative with respect to time of the magnetic flux. Well, I can see that it's easy to solve this for the magnetic flux, and that's just going to be L times I. So when I take the derivative with respect to time to that, again, since L just depends on the geometry, and once you build your inductor, you've sort of fixed what L is, then what's left that can change is the current. And so from Faraday's law, we can see that the voltage across our inductor, right, the potential difference across the inductor, is going to be given by the inductance times the time rate of change of the current. Now, a couple important things that this equation is trying to tell us. Well, one is that the current through an inductor can't change instantaneously. What does it mean for that to change instantaneously? Well, basically, if the current changed instantaneously, that would mean you're making this infinitely large. To make this infinitely large requires an infinitely large EMF. And so we know that we can't have infinitely large EMF, so that tells us that you can't change the current instantaneously. So what inductors fundamentally do is that they resist changes in current. So again, this is coming from the idea that what Faraday's law tells us is that, and again, sort of Lenz's law as part of this, is that things oppose changing the magnetic flux. So here within your circuit, what you're going to be doing is you're going to be changing the magnetic flux by changing the current. And so of course it's going to oppose that, your inductor is going to oppose that change. So inductors will resist changes in current. In terms of units, well, if we think about our definition here, it's just going to have units of magnetic flux divided by units of current. So that's Webers or Tesla meters squared, whichever one, divided by amps. And so what we end up doing is we define inductance in terms of a unit called the Henry. And so we'll talk about henries of inductance in the same way we would talk about ohms of resistance or farads of capacitance. All right, so from Lenz's law, that's sort of talking about how Faraday's law, what it tells us about an inductor. What Lenz's law tells us about an inductor is, again, we know that the induced EMF is going to oppose the change in the magnetic flux. So what does that mean? Well, partly what it means is it's going to oppose the change in the current. So let's assume, again, here's our symbol for an inductor. And again, you can sort of see the wire wrapping around. That's sort of where that symbol comes from. And let's just assume that this is hooked up within a circuit and current is flowing to the right across this inductor. So the induced EMF that you're going to get is going to oppose changing this current. So if what you try and do is increase the current, so you try and make the current flow more heavily to the right, increase the current as it flows to the right, you're going to produce a back EMF that's basically going to resist that change. And so here you would have an EMF induced within your inductor that would be trying to drive current to the left. If, on the other hand, you tried to decrease this amount of current that's flowing through your inductor, again, it's going to try to oppose that change. So if you're decreasing the current, it wants to keep the current value what it is, and so it would induce an EMF within your inductor that would contribute to the current. So the current that would flow, if you try to decrease, you would induce an EMF that would try and keep current flowing to the right. So again, this is the idea of how both Faraday's law and Lenz's law play into what's going on with an inductor. All right, well again, fundamentally we said inductors store energy within a magnetic field, so how much energy is stored within an inductor? And we'll start by thinking about the power. So we know that the power is the time rate of change of the energy, and I can calculate that for any of my circuit elements by thinking about the current times the voltage, so IV. And again, we're just using lowercase letters here because these values will change as the current changes within your inductor. Well, V, we said we could write that, right? The EMF induced across the inductor is going to be L times di dt. So I can write the power, so the rate at which energy is stored in my inductor with this expression. And so if I want to know the total energy stored, well, all I need to do is integrate this. So the total energy stored in this case is just going to be stored as magnetic potential energy, right? It's going to be potential energy stored within a magnetic field. And so to get that, I just need to integrate all these tiny little contributions to the energy as the current changes. Well, this is just another way of saying P dt, right? Because power is the time rate of change of energy. And so all I'm going to do is plug in my expression for the power. You notice that the dt here is going to cancel this dt there, and so I'm left with Li di that I'm going to integrate from 0 to some final current value I. L, again, that's just a constant, depends on the geometry, it doesn't depend on the current, so I can pull that out of the integral, and I di is just going to be 1/2 I squared. When I evaluate that from 0 to big I, what I end up with is this expression here. So the energy stored within an inductor I can calculate as 1/2 Li squared. And so those are sort of the fundamental basics with what's going on with inductors, and then we'll come back and talk more about what happens when we put those into circuits.